Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Hi, so it's with great pleasure that I introduce Melinda Tambe, who's here to lead the MSR Conversational Colloquium, which we encourage heavy audience participation, so please think of this as a conversation more than a talk, and feel free to address the points that he raises liberally throughout the talk. Melinda is a professor at the University of Southern California. I first became aware of his work when I was thinking about or reading about the applications of game theory to security in especially in airport security in LAX. So Melinda has a lot of very applied projects in using game theory to develop security for LAX, so that he's now extended to a wide variety of other applications, and even spun off a startup company that you can call up to get your security needs met as well. So I guess with that, I'll leave it to Melinda to describe the research to us.
Thank you very much for inviting me. It's been 2 really great days, lots of really fantastic conversations, and I thank you all for your very warm hospitality. Thank you very much. And so I'm going to talk to you today about the work we've been doing with security games, and I'm very happy to take questions as we go along. So this is joint work with a lot of people, a lot of current and former students and postdocs, as well as lots of other collaborators from around the world. And so that's our group. And since there's so many collaborators, to highlight the role of I'll keep highlighting the role of key students and postdocs as we go along. So let's just jump right into the topic. Security is a global concern. We have to protect our ports and airports, interdict the illegal flow of drugs, weapons, and money, protect forest, fish, and wildlife, suppress urban crime. And in all of these cases, we have limited security resources, a large number of targets to protect, and a watchful adversary who can monitor our defenses and exploit any patterns. So the question then becomes, how do you schedule or plan or allocate these limited resources, taking into account this watchful adversary? And we appeal to game theory, and in particular a model of a stack of security games called Stackelberg security games. Now, some of you may be very familiar with the Stackelberg model, but for the benefit of those who may not be, I'm going to use a simple 2x2 game to try to illustrate these concepts. So here we have the US Coast Guard trying to protect a toy port of 2 targets, targets 1 and 2. Target 1 happens to be more important here than target 2. Now, if as a result the Coast Guard say we will always try to protect target 1, then an adversary conducting surveillance will attack target 2 because the Coast Guard are at target 1. So the adversary gets a payoff of 1, the Coast Guard get a negative payoff -1. Now, the first number is always the payoff to the defender, the second, the payoff to the adversary. Now, if a result, the Coast Guard were to say, okay, we will always try to protect target 2, then an adversary conducting surveillance will switch as well. They'll attack target 1. The adversary again gets a positive reward of 5. The Coast Guard get a negative reward -5. So any deterministic strategy, the adversary could defeat. If the Coast Guard were to use a mixed strategy, a randomized strategy, so 60% of the time they're here, 40% of the time they are there, an adversary conducting surveillance will only know that they are here 60%, there 40%, but what they will do tomorrow remains unpredictable. The goal here is to increase the cost and uncertainty to an adversary in coming up with a plan of attack. We are not guaranteeing 100% security because there is no such thing. We are optimizing the use of our limited security resources. Now, these kinds of games are called Stackelberg games because the defender moves first. They're out in the open, they're patrolling, for example. The adversary can observe that and then do a best response. Now, the challenge here, of course, is that this is a toy example with 2 targets. In the real world, when we have trillions and trillions of possible patrolling strategies and very, very large numbers of targets, solving these games by hand becomes very difficult. And for a human planner, even if you say, okay, here's all the trillion possible ways of patrolling, come up with a randomized method, it's extremely difficult. And so this is the problem that we solve. And so in the initial part of our work, so we've been working in this area of security games. It's not only use of game theory and optimization, but also planning under uncertainty integrated into it and some learning. So the first part of our work, we solved massive scale games and reasoning with uncertainty were combined together in building applications that we now call infrastructure security games. So our work is in use by the Coast Guard in generating patrols in ports like Boston and New York and Los Angeles. So this is generating randomized patrols in the port, taking into account values of different targets. Or patrols around the Staten Island ferry in New York. The TSA used our work in assigning air marshals to flights on a randomized basis. And I'll talk more about that. All of this work started by early work that began at the LAX airport, which Nicole referred to, in generating checkpoints on roads and patrols around the airport. All of these games were solved as a Stackelberg game, and I'll go into that a little bit more throughout the talk. We take our own medicine, and so at USC, the patrols are also done using the same model. Yeah.
The interpretation of Stackelberg is usually a little bit ambiguous because sometimes it's viewed that the outcome of the randomization is observed by the downstream player, but you're assuming that you can commit, but that the probabilities of mixing are observed, but the outcome of the mixing is not observed.
Exactly right. So the interpretation here is that you're committing to a mixed strategy, and that's what's observed by the adversary in long-term surveillance. That's exactly right. And so it's spreading to other places. So our colleagues at the University of Buenos Aires have started to use it for generating patrols in Argentina, work going on in Chile, and so forth. So we're very thrilled with all the work that's going on in this area. Where we are going with this is what we've been calling green security games. This is protection of forest, fish, and wildlife, and rivers, and so on. So we're working with organizations like World Wildlife Fund, Panthera, WCS. Yes, please. Yeah.
Is there a sense in which mixed strategies don't really capture kind of how it works? Like if I have a guard patrolling 10% of the time, I'm not 10% safe. I'm significantly less safe. Or am I thinking about that in kind of the wrong way?
I'm not sure I understood.
Like, does it really scale with the level at which you're weighting these different options? So like, if you're just like not there 99% of the time, I'm not 1% as safe. I'm basically not safe at all.
So I guess, I mean, there's a one, if you are there, say 10% of the time, there's a 10% chance that you are going to capture. Now, what you might be referring to, I don't know if that's the direction which you are going, is the perception of the adversary. And that's a whole area that we've been investigating. Hopefully I'll come to that point a little bit later on. There's some very fascinating things about what we found seem to be quite contrary to what prospect theory says, for example, where how probabilities get perceived by a human being. But I'll hopefully be able to come to that point in the talk.
The question is related to Glenn's question. I guess the idea that if the Coast Guard is there 1% of the time, the adversary cannot predict
Which is the 10%?
which is the 10%, so they might be caught. So they only know that it's 10%, but they don't know which 10%.
But there's also the probability of the perception and probability weighting. So I'll come to that a little bit later on, hopefully.
Framework as well?
Say that again?
Do you you endogenize punishment?
So I guess there's this work on audit games, which is a whole derivative on deciding the level of punishment and things like that. But that's not something we've done. You're very familiar with that.
Yeah, audit games includes a punishment parameter as part of the defender's action space.
Right. But we haven't dealt with that. So this group has, so they know more. So what's different here when we are looking at wildlife protection or fishery protection and so forth, or for example, work with IBM on river pollution prevention, is the fact that there is here we have data. Unfortunately, there's a lot of poaching going on, and so there's lots and lots of data on poaching, which means that you can generate predictive models about how poachers behave. And therefore, it now becomes a repeated game where you generate a strategy, the adversaries react, you can collect data, and then use those models to play the next set of strategies. So here now, we start collaborating with people from conservation biology and conservation criminology and other disciplines that I didn't know existed. Beyond this, though, there's another data set when we start thinking about urban crime. And so this is work that we've recently started focusing on with data from LA. Unfortunately, no shortage of data on urban crime here. And so based on that, again, we can do predictive models. But given that I'm expecting a conversational seminar here, this and any work on cybersecurity and so forth, I'm not going to talk about. So hopefully, I'll just talk about this.
Predicting the adversary.
Yes, not adversary, friends here. No adversary. So all of this work in 2013 led to our startup, ArmorWay. So this was started with a competition at USC where they, after winning the competition, they gave us seed money. We started with 2 people, and who's going to be in the company. And then against my advice, 3 PhD students quit their jobs and are running the company. And it's growing, so now we have 12 people in the company, and it's a very exciting time. I hope they've made the right decision, and these are good jobs, so I'm really hopeful that this all works out. But it's a very exciting time in terms of where this is going. So USC also did a nice magazine article about our work, pointing out all the different places where the work was deployed. And particularly, you can see here work in Argentina and Chile with our collaborators and colleagues, and work outside with the non-governmental organizations. All of this work is possible, I should say, because of the interdisciplinary collaborations and our embedding with security agencies, and this is really important. And in the process, some of our students have had to learn new kinds of PhD survival skills that they didn't anticipate that they would learn during the PhDs. So in the rest of this presentation, I'm going to walk you through what we've done starting from 2007. And all of the work has been published in conferences like the normal AI conferences, AAA, HCI, HAMAS, et cetera, So if you want to look at detailed experimental results, like when we talk about scale up, does it really scale up? When we talk about handling uncertainty, does it handle uncertainty? All of those results are here. I wouldn't have time to go into that. But I do want to talk about, since we are fortunate enough that some of this work is deployed, to understand what impact has it had due to these deployments. I ask for your patience, though, because this I'll do right at the end of the talk. And so please just hold on till that time. And I promise I will come to that at the end. So let's start with air travel, which was our first work that we did. So this is our basic Stackelberg security game model. I present this because it's the first, it's also the simplest, and therefore easiest to talk about. And this work started because we were doing our normal multi-agent research when Errol Southers, who was the assistant chief of airport police at the time, had this question to us, which is how can we improve security at LAX? The threat here was something like this. A truck bomb in this case, attempted to be launched at the Glasgow airport in one of the terminals. So and by the way, Dr. Errol Southers was also later President Obama's first nominee to be the head of the TSA. And so we're very fortunate he decided to stay at USC, stay in LA, not go to DC. His challenge here was something like this. There's 18-bound roads into LAX, but where and when do you set up checkpoints, 8 terminals, where and when do you put dogs? We solved the problem as a Stackelberg game. And sometimes this schedule leads to arrest of people carrying large numbers of weapons into the airport, but I'll do a more thorough evaluation a little bit later on. So the way this whole thing works is we start with the game matrix. I'll come to how we generate the payoffs. This game is then fed into a mixed integer program. The mixed integer program generates a mixed strategy, which is a probability distribution. For example, it's saying at 8 a.m. at terminals 2, 5, and 6, there's a probability of 0.17 to have a canine patrol. At terminals 3, 5, and 7, a probability of 0.33 to have a patrol, and so forth. And then we sample from this distribution to generate an actual schedule. So it is saying at 8 a.m., Team 1 should go to Terminal 2, Team 3 should go to Terminal 5, Team 5 should go to Terminal 6. And at 9 a.m., something else should happen. At 10 a.m., something else should happen. And this is an actual schedule that is then given to the officers, and they execute that.
So I would attack at 8:99.
What?
When the teams are all moving around.
59.
Right. I mean, so that's a good point about where the sort of the movement times and so forth. But this is all a sample schedule for illustration purposes, not the exact thing that is given.
So in your example, you have a payoff matrix with some entries that came from somewhere.
Yeah, I'll come to that in a second where I got them. Yeah, just on the next slide. And in the next couple of slides. Yeah, that's a very, very important point. So let's go to the mixed integer program just to sort of give you an overview of how this might work. So we are trying to maximize defender expected utility. Rij is the reward to the defender if the defender took a strategy I and the adversary took a strategy J. Xi is the probability with which a particular strategy is played. So X1 is the probability there's a dog on terminal 1 and a dog on terminal 2. X2 is the probability there's a dog on terminal 2 and dog on terminal 3. So we're enumerating every possible combination of assignment of our defender resources to targets and assigning a probability variable to that. This is okay for small scale problems. It doesn't scale up, and I'll come to how we can scale up a little bit later on. Qj is the adversary's response. And this is going to be the adversary's best response. So we are assuming here that the adversary gets to observe our mixed strategy and then choose a particular terminal to launch a truck bomb at, for example. So I'm not going to be able to explain why this is the best response, but it is. And now the question is, where did we get these Rij values from, and you can't quite run this exactly. You have to do some tricks to get it to run faster and all that. But again, those can be done. So now, where did you get the Rij values? So in this particular case, the threat, as explained to us, was a truck bomb launching into one of the terminals, and therefore we took as payoffs the lives that could be lost if such an event were to happen. There's a detailed surveillance, detailed information available about how many people are there at different terminals of the airport at different times of the day, and so we are using that input in our payoff matrix. Later on.
Is this specific to a particular type of attack, like a truck bomb, for example? Do you have to do a different model if it's some other horrible thing?
Assault weapon.
I mean, I guess, there's a class of threats that would be captured here.
Yeah.
But I don't know if there's some chemical something threat. I don't know. So then that would be a different threat model, and there's a certain threat model that's captured here where and there's certain it doesn't capture everything basically, which is obvious.
I'm just thinking the attacker with the best attack is always to do something that nobody's thought of defending against. Right?
I completely agree with you. I think the main point it's very important to take away from here is that all we are trying to do is to increase the cost and uncertainty. There's no such thing as 100% security with limited resources. That's what we are going to be able to do. And the other point I forgot to mention earlier, which I want to make, is you might have seen earlier, I said ongoing, big red letters. And that was to flag the point that this is ongoing research. And so there's going to be questions, which I hope there will be. That will be new research topics, new PhD topics here that I hope I can take back with me as well. So there's a lot of questions that are unresolved, lots of things. Our standard here, as you'll see later, is really, have we improved the state of the art compared to what was being done by human schedulers and so forth before? And the answer there will be yes, but could it be improved? Yes, I already agree.
The key question is, you have to have multiple models for multiple types of attack.
For multiple types of attackers, yes, if they have different payoffs, we can do Bayesian games and all that kind of stuff. And actually this, in the end, was a Bayesian game. That's how we modeled it. I just don't have time to go through it right now. I'll sort of briefly touch upon it a little bit later on.
It seems you've chosen not to formulate this as a mini-max game. So it seems like the attackers might value things in a different way than the harm it causes to me. Can you comment on sort of why you made that choice?
So actually, many of our games are zero-sum games. And I mean, this is really, for a zero-sum game, Stackelberg model doesn't matter. I mean, the answer is the same. The strategy is the same. And you're right, once it's a zero-sum, if the adversary doesn't respond optimally, it's to our benefit. The reason this didn't go that way, the non-zero-sumness comes in, is that the thought is that even if we are able to capture the adversary, the loss to the adversary is not exactly our gain, because from their perspective, according to the modelers here, the people we were talking to, is that they still gain publicity. And that is not, that's still a positive outcome potentially. And therefore, it wasn't modeled as a zero-sum game. But it's quite close to a zero-sum game. And as a security game, there's always this property of the game, even if it's non-zero-sum, that anytime you place resources, we assume it's always better for the defender and worse for the adversary.
On the slide where he wrote down the best response constraint for the adversary, which has now been erased to make room for the picture.
Yeah.
Yes.
He was using the column values, Cij, not the row values. So the mathematical program that he wrote down interpreted the adversary's best response not as inflicting maximum damage on the row player, but gaining maximum payoff for the column player.
Yeah, no. My question is, why is it?
Because it's but I mean, if you make it a zero, yeah.
So maybe the example, if I understand correctly, suppose you had two terminals, one which has 1 person and one which has 100 person, then your loss would be 100 persons versus 1, but the adversary might think that they gain, that even if they attack just a single person, they still gain so much publicity. So they gain like 50. They get like 51 versus 101.
So that, I guess where I was going was, if they get captured, then in some cases we would say we've saved we've got 100 people that we saved, something like that. But from their perspective, the loss was not 100. Their perspective, their loss was maybe 0, because hey, they got, yes, their attack was foiled, but they got publicity.
That would probably be like just a fixed additive thing that would not change. You could still model it as a zero-sum, but.
But I mean, it gets into sort of very detailed things. If you get captured over here, does it matter? Does it things like that. But suffice to say, in most of the other games, in many of the other games, you'll see it's a zero-sum game. And with respect to the payoffs, later on you'll also see games done with the U.S. Coast Guard. There, incredibly, there's a team of researchers who's gone to all of the different major ports, for all of the different major targets, for all of the different methods of attack that they could possibly think of. So how many people would die? What would be the economic consequences? And they multiply the number of deaths with some number to get a total value of a loss for each attack. And that's the number that we use in our payoffs. And so there's this lots and lots of data that's available. But it's not exact, so just, and so we have to handle uncertainty, and I'll come to that a little bit later on. Go on, please.
So I'm very curious about some of the implicit value judgments that go into making the entries of this.
Yes.
So for example, if the defender's utility is interpreted as the number of lives saved, then it could be that a defense strategy that says stop every car whose driver has a beard maximizes expected utility under that notion of utility, but okay, we may have other reasons not reflected in the payoff matrix why we think the societal consequences of adopting that policy.
That's right.
Would, undermine the benefits. So I'm curious, in the institutions that you've interacted with to design these games, do they incorporate those kinds of value judgments into their reasoning when thinking about how to structure the payoff?
So I guess there's 2 or maybe 3 answers I want to give. One is that they like these tools because precisely they move away from human judgment, at least in some of these respects, because now you have the program saying, okay, this is where you're going to be set. It's not going to be based on potentially their biases.
If the program ends up being racist, then they kind of have
Right.
Hey, it wasn't my fault. The program did it.
That's and I mean that's
might not be one of the rows of the matrix, right? Because it might
right,
be
and
strategies.
so I mean that goes to some very, very interesting questions. I'm on this AI ethics report panel where all these. I mean, we aren't there yet in these things. I understand the potential warnings you're giving that if you have. You're doing I mean, in this case it is not, but later on when I talk about predictive crime, that this type of thing might happen. You sort of focus on, okay, that's the neighborhood, and that's a danger that we really need to worry about in the future. But at least with respect to these things, these are valuing things at a much higher granularity, and so they aren't really coming, the program itself is sort of saying things at a much higher level of granularity, like, be on this road at this time. It's not sort of saying this particular person. Now, this also means that there's a certain interface between the program and the human being who's working this. And so this is carefully manufactured so that there's a certain level at which the program stops recommending anything. So it doesn't say this car, it just says, at that point it's not saying anything. And that judgment is ultimately left to the human. So the other thing is, the fact that this program in that sense is open, it's not, I mean, everything is published and so forth, is seen as a good thing because they view it as it's like we can publicize this, it may act as a deterrent, but there's nothing secret in the program that's being, so it's not based on sort of secret, guarding secrets. So anyway, so after this program was working, wow, it's at this rate, it's a very conversational seminar. You had told me this, but I didn't realize how conversational it is. So I'll have to sort of speed things up quite a bit as we move on, but it doesn't matter, it's fun. We'll get through whatever we get through. So in 2008, after having this program work at LAX for about a year or so, and other improvements Errol had made, he was called before a congressional subcommittee hearing, and I'll just play like 50 seconds of his testimony.
LAX is safer today than it was 18 months ago. A team of research led by Dr. Milen Tombe worked with our department to develop armor.
And then he goes on to explain how armor works. And then around the same time, we had some media coverage like this. So, at the next AMAS conference, our colleagues were asking us how our cloaking device research at USC was coming along. But it got us an invitation from the TSA to go visit the TSA Freedom Center. And this is in front of, this is a thing made from parts of the airplanes that crashed into the World Trade Center, a beam from the World Trade Center, rubble, and so on. So at this point, standing in front of it, our armor program, if they ask us to make it work here, really must work here. So, and then they presented the problem to us, and the problem was something like this. How do you assign air marshals to flights on the international sector? There's 1,000 flights a day. We had worked on Armor 100 action game, and here the game, if you looked at it, was 10 to the power 41. And the reason is you think about 1,000 flights a day, 20 air marshals, and forget all the tour constraints and everything else. The problem becomes very, very large. And essentially, if you just feed the program into input into Armor, it quietly dies running out of memory. So we clearly needed a different approach. And here, the idea is incremental strategy generation, that is to not enumerate all the 10 to the power 41 different actions. So if you write the game in the normal form, to understand why scale-up might be difficult, there's 10 to the power 41 different rows in this game matrix assigning. There's 1,000 flights, 20 air marshals, that's 1,000 choose 20. You might assign air marshals to flights 1 to 3, 1 to 4, 1, 3, 5, so forth. There's 10 to the power 41 different rows here. The adversary could attack flight 1, flight 2, up to flight 1,000. This program cannot run because there's 10 to the power 41 different xi variables, one for each possible row. This program cannot run, but if we could make it run, what we would find is that many of these xi variables are 0. In fact, most of them are 0. In fact, we can prove, as you might imagine, that there exists a solution with a very small support set size. And therefore, if we can eliminate all these xi variables magically beforehand itself, we would have a very small game matrix, which if we solve, we would get the exact same solution as we would for the large game matrix, which means that we can now take an iterative support. So we start with a master program that has a small set of pure strategies, and then use a slave that using LP duality theory gives us the next best pure strategy to add. It's column generation, if you're very familiar with mixed integer programming. Basically, this is branch and price at work. And then at the end, what you get is a global optimal solution, but here we have a very small game matrix, maybe with just 500 rows that achieves the same global optimal as the massive program before. And this is what is in work in IRIS, which is a program that's used to assign air marshals on an international sector. It's led to significant change in the FAM's operations. If you've been on an international flight by US air carrier, whether there was an air marshal or not on your flight, was potentially, possibly decided by this program. Go on, please.
Structure that's sort of like quasi-additively separable across the different planes to which you allocate the air marshals. So it doesn't seem like it actually requires you to. Is that what's being put into this slave that's reducing the set of policies?
Yeah, it's. I mean, the slave is doing some kind of flow it's doing a max flow problem. A network flow problem is kind of assigning air marshals to flights, and then it comes up with the next best pure. It's next best pure strategy to add. There's a little bit more complicated thing going on here because you have to think about there's a tour, and it's not just one set of flights that are going, and so there's a little bit more. So it's not a very easily structured problem. There are complications that arise if you try to solve it using, assuming that there is no tour and things like that.
So, just maybe, I don't know if that's what it means with quasi separate, but if you try to solve it by, say, first assigning one air marshal greedily to the best flight and then the second one to the second best, etc., so it will not be.
It will not work. It will not work. And I think part of the reason there is the tours that kind of make things complicated. So anyway, so this is just another congressional subcommittee hearing. 2011, the Mars Society selected a University of Southern California project with FAMs on randomizing flight schedules for the prestigious RIST Award. So we were happy to hear that. Now let me, given the amount of time left, try to walk through some of these things a little bit faster. So I'm going to talk about a new way of scaling up. This is the use of marginals. This is work we did with the US Coast Guard. This is a system called PROTECT. PROTECT is an acronym. This is to tell you we spend enormous amounts of time coming up with good acronyms, usually 2 hours before the deadline. And so this is generating patrols around in different ports, patrols around the Staten Island ferry. The threat here is somebody launching an attack either on the ferry or in one of the targets at the port. This program started in 2011, generating patrols, started at the port of Boston. 2012, the Coast Guard were happy enough, and I'll talk about some of the metrics they used a little bit later on. So they created a small video. I'll play a few seconds of that video, 50 seconds of that video.
The result was invigorated boat crews more focused upon providing effective presence, reducing predictability, and enhancing the safety and security within our ports. Protect guided patrols became a source of pride for Station Boston crews, and it doesn't get much better than that. Protect has also had other positive side effects, such as the development of better tactics, techniques, and procedures. The results have been exceptional.
And following that, we started working with the Staten Island Ferry, carrying 60,000 passengers a day. The threat is somebody launching a suicide boat into the ferry. So here is the Coast Guard patrols that run around the ferry. These are our algorithms at work. And it's a game that's solved in continuous time. I'll talk about that next.
This patrol is observable.
Right. So,
I see that there's a patrol there, so I wait for the next ferry on the next hour.
Right. So I guess the idea here, you're absolutely right. So there is this sense that, here the whole thing in all of these models is the following assumption, that you have a mixed strategy that's going to be played, and it's just going to complicate the adversary's planning with respect to plan of attack. Now, if you do allow for this extra thing that they are going to wait, and allow for that uncertainty in their plans, and they can observe and then react, then that leads to a more complicated model. There's papers on that as well that we worked on. I'm not presenting them here. That's not what's implemented, but you're right. So the assumption always here is that we are saying that the adversary would abhor that uncertainty, and therefore we want to create these randomized patrols around the thing.
Maybe the flip question to Nicole is that so much security strategy is about making it appear that there's more coverage than there is.
Yes.
A very limited, number of bodies than the, very visible security cameras or a sense that people are there. So this is still mapping on, like, if you have one body, you can put one body in one place. How do you factor? Is there a way to think about the kind of techniques about making those things visible? And not just like you can put up cameras, but for someone to believe those cameras are effective, they have to know that when an incident happens, people do show up. So then there is a use of manpower in that incident. Right.
So it's sort of more of it could be even extended to decoys to improve security effects. And I'm not going to talk about, there's some work that's gone on into that. It's a fascinating question, lots of questions. But one thing here that I'll not get to is evaluation later on, where one of the things that we heard, the Coast Guard here have heard, is the fact that operation hours were cut down, but people asking them, have you purchased more boats after the Protect system was deployed? And in fact, no more boats were purchased, but exactly this effect that there's just more presence seen on water.
Off the video, people were talking about how proud they were to be using this new system, and I would have thought actually that that I might be unhappy as a worker being told where to go and which algorithms to run, losing the sense of agency. And so I'm curious.
It's like SMC is in the house.
I was actually thinking of asking the very question here, but still.
This is actually Sarah's expertise.
Well, Sarah's in this case, yeah, right. So but you didn't find that experience, or you didn't really hear about it?
No. So this is the interface that there's always a negotiation. So we start out sometimes going too far. So we will tell. It start, for example, here in Boston, go to this exact coordinate, then go to this exact coordinate, and then there'll be like no, that's too much. We know our port, so give us this area. Then we can. But there's a sense of. It's been this thing starting from Armor, that being involved with this whole software and so forth, it just seems like it works well for the officers. It excites them just as much as it excites us, and it is just sort of a very synergistic interaction, and it's been fun that way. So we haven't. So there is but there is that negotiation, and this technology adoption issue we were just talking earlier. It's so fascinating. I'm sort of debating whether to discuss that or go more through my talk. But let me just go through my talk, because that's a whole very, very interesting thing to discuss. So let me just push ahead here, and then if time remains, I'll chat more with you. So I just want to very quickly show you the discrete space-time representation. There's a continuous time improvement of it in the Journal of AI Research 2013. I'll just use this so that we can go through this quickly. So this is, ABC at 3 locations, 3 different time points. A ferry here can jump from C to B to A, so it's jumping at these 3 locations. You can have a patrol boat doing a patrol here, starting from B, going to C, going to B, this green patrol boat. And a patrol boat protects the ferry right next to it. And so we can solve this game as in Armor, and we get a probability distribution over the different routes. The green route has a probability of 0.23, brown route probability of 0.47, and so forth. We could do this, but this is very expensive because there's exponential number of patrols. Each patrol here is a variable. There's n to the power t variables. But instead, if we now take probability flow over individual segments as variables, so we combine the green and the brown segment and call this one probability variable, the 2 blue segments call this one probability variable. Now we have n squared multiplied by t variables. We can solve the problem and then sample from this and get what we ultimately wanted.
I think that's exactly what I meant by quasi-separable in the previous problem, was just thinking about each flight as a marginal rather than thinking about all.
Right. And in fact, in this paper, we say exactly additive separable utilities. So you're exactly right. But in the air marshals, the fact that you have these tours just make things really complicated. So that's, and we have a theorem that if the air marshals don't have to return to the United States, then we can really speed things up. But of course, that's not acceptable. So, sometimes you'll see this. I feel safe. It makes us feel nice. And then this is the U.S. Coast Guard in the Congress.
We're working with the University of Southern California to utilize game theory as a way of optimizing and scheduling our patrols.
And he goes and talks more about game theory. But for those who work on game theory, hopefully this gives you some value to seeing game theory in use. So I will now switch and talk a little bit about use of trains here. The main issue is one of uncertainty. So checking ticketless travelers on train was the next application we looked at. We said we could apply a transition graph representation, send schedules to police officers. 9:15 a.m. start at this station, start checking people. 9:25 get on the next train, start checking people. And they have a paper schedule. Everything is going smoothly. My student is with the police officer. Things are going fine. At 9:24, just before boarding the train, the officer says, I have to take a bathroom break. Now, we can't tell the officer there is no bathroom break in a Stackelberg equilibrium. We have to somehow handle this uncertainty. The more serious issue there is the fact that they may arrest people sometimes. And that means all our optimization is all out the window. So we need some way to handle this uncertainty. So we want a probability flow of 0.30 here, but there is a small probability of 0.05 to remain here itself. This can be done by integrating Markov decision problems into security game framework. What this means is now each policy in MDP is a pure strategy in the game. So once we solve the game and so forth, we can load a solution on a smartphone, so they always have an action to take even if there is interruption. So, but this is only one kind of uncertainty, action uncertainty. There's uncertainty in payoffs, there's uncertainty in how much surveillance is going on, uncertainty in the amount of rationality an adversary may bring to the table. So we have generated algorithms on each of these frontiers. Lots of PhD theses in this area have been done, more need to be done. More recent work has started to unify these into one single algorithm. So let me now go on to what I think seems to be of interest based on my conversations here to a lot of people, which is protection of forests, fish, and wildlife. And so I'll skip the part here, which is talking about sort of things generally about protection of forests and fish, and get wildlife protection. So this is Murchison Falls National Park in Uganda. Some of you may have been there, but if you haven't, awesome place. I was there in fall of 2014 to establish our collaboration. And you can see amazing wildlife, but there's threats to the wildlife. So for example, these are snares. The way this snare works is that they bury it in the ground, they open the jaws, if an animal steps on it, it closes, and then a poacher comes and kills the animal. These are thousands of these snares found just in 2014 alone. So this is me with the head of security of Uganda Wildlife Authority in the park. And the way he explained they work is they'll send out patrollers in the forest. The patrollers will collect data, collect snares, they bring them back to headquarters, they'll analyze, kind of figure out what to do next and send patrollers back again. So this will go on month after month and so forth. So we can model this as a repeated game. So we have here the forest divided into a grid. Each grid cell is a target. Cells where there's a lot of water have high value, more animals. And we are going to generate our strategy, execute it. When poachers attack targets, we can get crime data. From that crime data, we can calculate our mixed strategy and continue to improve things. So we need to learn bounded rationality models for our poachers. So I'm going to quickly run through this part and then come to the final part about evaluation. So whereas one way to do it would be to learn from data, and we have a lot of data. Another is to play a game on MTurk. That's what we've done, a simulation game where people act as poachers, our algorithms act as defenders. And so people can go to different sites, see what's the probability of capture, what's the reward, what's the penalty, and they place a snare and they succeed, they get real money. If they place a snare and they fail, they lose money. And we've been playing these games for the past several years, trying to collect data on how humans play these games. And of course, if we assume people are perfectly rational, they would calculate their expected utility, capture probability multiplied by penalty, etc. And everybody would go and attack the one cell which has the highest expected utility. But in reality, attacks are spread all over. And the model that seems to capture better at first is this quantum response model, a stochastic choice model, which means that if
This just indicated that this is actually not a rational strategy, right? Because I know that there are other agents around, so if we don't want to all attack at the same place, we want to agree among each other that you get that territory, I get
but there is no, I see. But in this particular game, there is no competition. So if we both go to the same place, the way we modeled it, we both win. If there's no patroller there. So, right. So they have some, but the areas are large areas here. What we're modeling are over kilometers of areas. There is that effect. That's just not. I guess let me answer it in two ways. One, we haven't modeled that, and secondly, I think the impact of that competition, even if it's there, the areas are really fairly large. So I'm not exactly sure how severe that impact would be. But we can discuss that.
If you would fight drug crime in cities, that would definitely be an important point, because you will have different drug gangs which actually sort of don't want to encroach on each other's territory, and you would not get this kind.
Right. No, I agree. Let me just push on here. We should let me discuss this later on. So if we assume that the adversaries have this model, if a target has higher expected utility, they're most likely to attack, lower expected utility, less likely to attack, and then play games against human adversaries. These are 4 different payoffs. We have many other games. Y-axis is defender expected payoff. Lower is worse, higher is better. If we assume the adversaries are playing perfectly rational, that's blue, that's the worst. If they're playing green, it's epsilon optimal, it's slightly better. But the best is assuming that the adversaries are playing according to this quantum response model. We can improve upon the quantum response model by using what we call subjective utility quantum response model. This is saying that the capture probability, reward, and penalty are 3 separate features of the game. And people are sort of looking at capture probability as independent of the reward and penalty, and then we learn these weights from previous data. And now, using the same kind of model, we generate this subjective expected utility. And so this turns out to be a better predictor of how people are playing. I'm going to skip a lot of things now because I don't want to finish on time. And I'll just show you some data. We have 12 years of patrols, 125,000 observations.
You said that you pay a lot of attention to engineering your acronyms to be pronounceable. So is this the sucker model?
Yeah. This one we were not so good at. I think Thine Win, who created this name, she should be told this, that this is not good. Improve it or no PhD. Yeah. So in this model, what she's done is taken this data and look at all of the different features of each target. But now we also have to be concerned about the fact that even if there's a crime, you may not actually be able to see it. So using this, we are able to show that this PAWS model, so this is Protection Assistant for Wildlife Security, PAWS. So we're improving there. That our PAWS model here for predicting poacher activity is superior to other machine SVM, Logit, and there's other models that we have. And so this is for dry season, June to August 2008. We have this for every season since 2008 to 2014, and showing that for each of those, we do better job predicting than all these other models that were out there. And so there's heat maps. So based on this, we generated patrols. They were first tried out in Uganda, then tried out in Malaysia. As you can see here, poachers camp found in one of the patrols. But not all was going smoothly. They would keep saying that you're not paying attention to geography. We were in LA, they're in Malaysia. They keep telling us shortest distance between 2 points is not a straight line. And we are, how's that possible? So we went to Malaysia ourselves to patrol in the forest. You can see this is the beginning of the patrol, how happy we are. That's me, my student Faye, former student Bo. And we started these patrols, hacking through the forest. There's a poacher's camp, and that's at the end of the patrol, 8 hours, thoroughly exhausted, and the guide saying there's 500 more meters to go that way. But at the end of the patrol, we understood the shortest distance between 2 points is not a straight line. If you look at it on a Google map, basically what we can see here is that really there are ridge lines and there are river beds, and to really walk in a way to avoid energy consumption, you have to follow this highway map that exists underlying in the forest. You can't just go anywhere. And so we took into account this highway map that is hidden in the forest, and that leads to a better patrolling strategy. So this is more planning rather than, let's say, game theory, but it's an important component of planning. So, so we have the system called PAWS, which takes into account species, location, uncertainty, all that generates patrols, deployed in Malaysia, tried out in Malaysia. We are working with WCS to get it used in Uganda. So this is under evaluation. We have data in one of our recent papers that shows that compared to their patrol routes, if you look at animal science scene and human science scene, that our patrol routes were better. But this is a small sample at this point. So we aren't, so we are always comparing with the human experts, and that small data shows that. But where we are better, where we will be better at, is more the randomization, the fact that we'll be able to more generate coverage.
The other question I had is let's say that I don't have access to your program.
Yeah.
But I want to sort of have some rules of thumb for my, for my guards to sort of replicate it, maybe not perfectly, but sort of do pretty well. Have you checked whether there are some sort of heuristics which they could improve on what they did before, but which could get close to what you're doing with your program? Because, maybe not everybody can do this, or maybe it takes time to implement it.
Right.
Maybe there are sort of simple things you can do to make things, approximately optimal.
So, really excellent question. But since I have 5 more minutes left, let me walk through the last few of my slides, and then if you have time, we will chat later. So just 5 more minutes. I wanted to talk to you a little bit about the evaluation that we've done. And obviously, this is trying to understand how well have those games performed in practice. And what we are trying to show here is, have we done a better job evaluating the use of, so have we done a better job using the limited resources compared to how that was being done by human schedulers before? That's the test. And we can certainly do a lot of simulations and human subjects in the lab, but we've also gone out in the field and looked at patrol quality before and after our software was deployed, and also field evaluation testing against adversaries, looking at capture rates of real adversaries. And what we can show here is, indeed, in all of these measures, we've done better than how human schedulers used to do this before. I'm going to have time just to show you some limited set of results. This is from the Port of Boston, day 1 through day 7. On the y-axis is how frequently did a boat go and visit a particular target. So how frequently did a boat go and visit this blue target? This is over many weeks. Somebody went out and looked before Protect was deployed, how frequently this was done. You can see 2 main points here. First, there's very few patrols on day 2. And secondly, all these lines crisscross, meaning sometimes a target was more important, some day the same target became less important. The targets actually don't change their value day after day. This is after Protect was deployed, the more important targets are visited more, the less important targets are visited less. On any given day where the boat will go remains unpredictable, but the more important targets are visited more frequently. And certainly anything like a dip on day 2 all goes away. If you look at it from a perspective of Defender expected utility, there's a 350% improvement in Defender expected utility. I wanted to very quickly tell you about, for example, for the FAMS, there's a 6-month competition, human versus machine, at the end of which there was a conclusion that the machine had done a better job scheduling. This is not surprising if you think about a human being looking at thousands of flights, trying to schedule with all the different rules, covering high-risk flights, and being random. We've done human versus machine competitions in.
How do you measure performance evaluation like that?
You can look at how predictable is the deployment, for example. And the human deployment is completely predictable. You can look at the coverage, which flights were covered, and human deployment is more focused on particular. And this is not me saying it. There's a Government Accountability Office report that points out these weaknesses.
There's no way to get ground truth on like number of attacks thwarted or something.
Right. So let me. That's right. That's right. So the one, I mean, there's many other things. Let me focus on this one study, and then after that, I'll stop and take further questions. So we went out on the trains in LA trying to check who can catch more fare evaders. This is an experiment we can do. So on the one side was the officers got their schedules on a handheld device. One was done using uniform random, one was done using game theory. They just didn't know which one was which. They were asked, if you don't like the schedule, you can go and interrupt it and go somewhere else to catch as many fare evaders as you want. And we did 21 days of patrol, identical conditions. What we found is that when we were given uniform random, the officers often didn't like it and they went to some other place. But when they were given a game theoretic schedule, they always stuck to the schedule. And at the end of this period, we looked at how many captures were there per 30 minutes. And we found that the game theoretic one led to higher capture rate than this combination of uniform random plus humans saying, no, I don't like it, I want to go somewhere else to capture.
This is 30 minutes for one person?
No, how many captures were there per 30 minutes?
30 minutes totally over all officers?
That's right. I mean, we weren't doing like a very, very large number of officers, but so there's roughly 15 fare evaders captured, per 30 minutes, basically. And so this is showing some, so where there is low cost, low consequences, we can certainly do these kinds of studies. We've done other studies, but since it's 5 o'clock, I'll stop here and take any questions you may have.
Why do you think people like the game theoretic randomness versus the uniform randomness?
I guess when we've accidentally tried uniform random in some other places, there's uniform random means it's really trying to send people everywhere. And so people will be going to, in airport setting, terminals where there's nobody there. And there's immediate sort of feedback that this program is doing. It happens once, okay, but if it just happens again and again, people can sense this. And similarly here, you're being sent to places, there's not many passengers there. They know that they aren't going to catch many fare evaders. And so this is a real test. They're really trying to catch fare evaders, and so they didn't like it.
So in terms of evaluation, I think it would be most convincing if you could do it. So once you have implemented the program, to have one area of the park that they still use the manual methods, and because one thing is like, if you compare before and after, is not really so convincing, because in some sense, the parks that are sort of deciding to implement your program, they might change all kinds of other things. Why they maybe get serious about going after poachers, and so you might find these differences even if so just to be devil's advocate.
No. I mean, on the poaching side, the work is relatively new compared to the other work that's been going on for more years. And so we haven't had an opportunity to really thoroughly evaluate things like the way you're suggesting. And that's, that would be kind of the ideal world situation where we can compare areas of the park. And that's partly what we are trying to do with WCS in Uganda, is to say, okay, can we focus on an area of the park where we can do this, and then potentially compare the results and so forth. But we haven't done that. So the results that I show, I mean, so just for example, so there are other things we have done where we can compare things. So this is one comparison. The other thing we did was, trying to have 90 officers be scheduled on the train lines in LA. And so this is, again, here's a game theory schedule, here's a human schedule. You have outsiders who don't know who scheduled which, trying to evaluate who did a better job patrolling or generating patrols. And on the 12 questions here, a game theory patrol, according to the humans who are judging this, did a better job than what the human schedulers had done. So consistently, human beings take a lot longer because they spend time generating schedules for 90 police officers on trains. It's not easy. And they generate worse schedules. And so so if you look at it from the perspective of, you have a human being who's doing this very complicated job, could they be just out there doing what they would like to do rather than scheduling? And the quality of the output that came out, the program saves time and produces a better output. So I don't know which way to go.
Really interesting talk, thank you. I think the thing that's really popping up for me as you're comparing the examples is that poaching may be a case of you have a lot of coordination that's happening among the groups who are doing the poaching, and it's repetitive. So it's a different dynamic than fare evaders, who are mostly individual agents who aren't trying to optimize in relation to each other. So as you're thinking about the poaching problem, I'm just seeing all layers of things that have to anticipate a deep amount of coordination that's even different than the cases where you've got a bomb going in. That might be a lot of intense coordination, but there's no sense that I have to repeat that over time, right? So just a thought when you're thinking about the
right. And I guess so there's this Netherlands Crime Institute where our collaborators is located. He's the one, and so they think a lot about these methodological issues and how, all these how do you do careful experiments. And I completely agree. I mean, it's if you use different areas of forest, could it be, is there some leakage effect going on? If you put pressure on one side, maybe you're just pushing people on the other side. So it's not really, so maybe that kind of effect. So I agree, it's a really interesting and complicated question, and lots of research issues. As I mentioned, ongoing, there's tons and tons of research problems, and I guess one of my secret agendas is that I can get more people to not work on ad auctions and work on this.
That would be awesome.
Maybe one last question?
Yeah.
For the airport security setting, since that's been running the longest, so what kind of evaluations do you have for that?
So I guess there we've done lots of simulations and all of those kinds of things. The only data that we haven't done a sort of a side-by-side study, the only data we have so far is this. This is not a controlled experiment. So this is before our software was deployed, numbers of arrests of drugs and firearms. This is after our software was deployed. You can see the numbers of arrests going up. Then at this point, newspaper articles start to come out about the arrests, and then the numbers of arrests start going down. Now, that's what we have. This is not a controlled experiment because we couldn't, we couldn't do this kind of a test there because you have the system whole operating. What we should, it's like some days you should do this, some day you should do that, but it gets really complicated with these checkpoints. But that's the data we have, and that's what I wanted to show.
Okay, let's thank Melinda.
Thank you. Thank you for inviting me. Thank you.